Okay, 3 rules of thermochemistry. The first rule is one that we've been using, and that is that the amount of heat produced by or absorbed by a chemical reaction is directly proportional to the amount of reactants or products. This is what you use this rule to complete that worksheet. The amount of heat produced or absorbed by a reaction is directly proportional to the amount of reactants and products. And so that's why we can use, that's why we can do worksheets like this. If you take, say, something like this, this is just an example. This was liquid, right? 591.6, is it? I think that's right. So the amount of heat produced by this reaction is going to be directly proportional to the amount of reactants or products. So if 1 gram of H2 reacts, we just do it like this. We turn this into, we have a gram of H2, and we turn it into moles. Turn that into moles. And let me get my calculator going. And then we can convert it into heat by using this sort of thing. Now, just to reemphasize, notice this. I take this, and that goes there, right? And then I take this, and it goes down in the bottom. Notice the 2. Very important. So here I've got 1 gram divided by 2.02 times 591.6 and divided by 2 gives me negative 146. So this is all, the rule number 1, that's all it's talking about. Yes?
Why did you make it negative?
I made it negative because, recall, if this were written, I could also write this reaction like this. If I were to write this as delta H, I would write it as a negative. Because the reaction is giving off the heat. It's producing heat, which means heat is going out from the reaction, which means the reaction is losing heat. Really, what delta H means is the reaction is going down in potential energy. So if I were to draw a graph, I'd have 2H2 plus O2 up here, and I'd have 2H2O down here. Right? So there's a negative change in potential energy. So that's why it's negative. So that's the rule we've already covered. Number 2, we've actually, I think I had mentioned number 2 before, and that is that the enthalpy change for the forward reaction is equal in magnitude but opposite in sign to delta H for the reverse reaction. And I didn't state this before, I don't think, but I showed you that if you flip the reaction around, then whatever would have been produced is now being absorbed. Reverse, sorry. Reaction. All right. So, for example, I showed you this demo with the forks, right? Whatever energy it requires to split the water into hydrogen and oxygen, that same amount of energy will be given off when they reform water. So I could write it like this. I've got 2H2 plus O2 gas yields 2H2O liquid. And then this is delta H is equal to negative 591.6 kilojoules. And if I turn the reaction around, all I'm doing, I'm writing the same thing, I'm just writing it backwards. I'm switching the reactants and products. Then delta H is equal in magnitude but opposite in sign. Same number, different sign. The sign tells you whether the heat's going out or coming in, whether it's being produced or absorbed. The negative sign indicates exothermic. Did I mention that word before? Video did? Yeah. And the positive sign, endothermic. But notice that they're equal in magnitude. It's the same reaction, only backwards. So the amount of energy is the same. And that's because if you look at the energy diagram, it's just a matter of whether you're going down or going up. The distance is the same. Let me show you another example that's kind of interesting. Very common, but pretty interesting. Let's take solid water and turn it into liquid water. Turns out that delta H for this process, well, what do you think? It's 6 kilojoules, but do you think that this should be negative or positive? This is what's happening here. It's solid water becoming liquid water. It's melting. Melting ice. Positive? Right. Yeah, so it's absorbing heat. So in order to melt ice, you have to put heat in. Okay, think about that for a second. If you want to melt ice, you got to put heat in. So it's going to be a positive delta H. Okay? Now here's, I don't know why this can be confusing, and maybe it's because if I had an ice cube in my hand, what's it going to feel like? It's going to feel like cold, right? It's going to feel cold is what I was getting at. Now, yeah, it's going to feel cold. Why does it feel cold? Because heat is going out of my hand into the ice, okay? My hand is losing heat to the ice. The ice is gaining that heat. It's gaining potential energy, okay? Now watch this though, this is a little weird. Liquid water going to solid water. Freezing. According to rule number 2, this must be negative 6.00 kilojoules. So listen to that. That is what this is saying. You don't get why this is weird. So what I'm saying here is when water freezes, it gives off heat. Okay, if you don't think that's weird, that's fine. That's great. It turns out that, yeah, so when the ice cubes form in your freezer, folks, when the ice cubes are actually freezing in your freezer, they are actually giving off heat. Now, it does make sense when you think about it. Let's say your freezer's working, it's pumping the heat out in order to bring the temperature of the water down to 0 degrees C, okay? What we're really saying is once the temperature of the water in the ice cube tray gets down to 0, the pump has to keep pumping heat out to turn it into ice while it's still 0 degrees C. And that takes 6 kilojoules per mole per 18 grams of water to just freeze it. And at that point, it's actually not changing the temperature, it's just changing it into a solid. I always tell the story of Dr. Bent's experiment in his basement. He has a real drafty house, like an old house with like a stone foundation. And he has a problem where his pipes often freeze down there because it's so drafty. So he had an idea. What he was going to do is put a kiddie pool in his basement filled with water. And the idea was that as the water froze, so let's say the temperature's going down, okay, and the temperature gets to 0 degrees C in his basement. Well, he doesn't want it to go below that, because if it goes below that, that's when his pipes will freeze, right? Because, I mean, if he keeps the water running a little bit, it won't be too bad, but if it gets really cold, they'll freeze up. So here's what happens, though, with the kiddie pool down there. It hits 0 degrees C, and it starts to freeze, okay? As the water's freezing, it's releasing heat into the atmosphere. Now listen to this. This is a little weird, but that heat, cannot raise the temperature above 0. Because as soon as it did, it would stop freezing. You follow me? It's at the freezing point. As it's turning into a solid, it's releasing heat. But that heat cannot raise the temperature of the air above 0, because if it did, the freezing process would stop, and so would the heat. Right? So the best it could do is keep it at 0. Follow me? It could potentially keep the heat at 0 if cold air is coming in through the basement walls. So he's got these stone walls. If cold air is sailing in through here, let's say it's minus 10 degrees C outside. Cold air is sailing in. What the freezing could do is heat up that cold air to 0 degrees C. All right? And keep it from going below 0. It didn't work. And I guess it was because there just wasn't enough water. It froze and yet still got colder than 0 in there. It must have been just too much cold air coming into the basement. I mean, if there's a constant flow of cold air going through here, you basically can't warm up the entire eastern seaboard of the United States. So it didn't work. But it was a good idea, right? So rule number 3. Any questions on rule number 2 before we do rule number 3? Rule number 3 uses 1 and 2 together. Okay, so it uses rule 1 and number 2, and rule number 3 has a special name. It is called Hess's law. Hess's law. And here's how I'll state it. If reaction number 1 plus reaction number 2 equals reaction number 3, then delta H number 1 plus delta H number 2 equals delta H number 3. Now, let's look at a common example of this. We're still in chapter 11. The entire test next week is going to be just in chapter 11. In fact, we're not even going to cover all of chapter 11. So it's going to be kind of a little less info maybe than usual. Now this is kind of, a lot of reactions actually happen in steps. So let's look at an example of what I'm talking about here. Reaction 1 plus reaction 2 equals reaction 3. What I mean is, say the reaction happens in steps. So I want to burn carbon. So maybe this is charcoal. Maybe it's the graphite in your pencil. Maybe it's a diamond that I want to burn. Right? So I got a carbon, solid carbon, and I'm going to combine it with oxygen gas. It's combustion. And I'm going to get carbon monoxide gas. Delta H for that is 110, right? Negative 110. Yes, negative 110 and a half. See that? So that's the formation of carbon monoxide, and that's what happens. That's actually the first step in the combustion of carbon. That's what's happening when you look in your fireplace and you see the red hot coals, that is what's happening right at the surface of those coals. This first step, and it makes sense because first the carbon is going to get one oxygen, then it's going to get the second. Okay, so the second step is when you add the second oxygen to the carbon. So we're going to start with this one, carbon monoxide. We're going to add one more. Notice I have 1/2 here. These are on moles. It's talking about moles here, so 1/2 mole. I'm going to add another 1/2 mole of oxygen, and I'm going to get a mole of CO2 now. Carbon dioxide. That completes the combustion process of carbon. And this is negative 283. Now it turns out you can add reactions just like you could add equations. So here's what I'm going to do. I'm going to add these two. Now to do that, I'm going to put my arrow here, and I'm just going to write whatever's on the left. I'm just going to pull it, I'm going to carry it down to the bottom and write it again. So CS 1/2 O2, CO 1/2 O2. So I took everything on the left and I just pulled it down to the bottom. I copied it down onto the left. I'm going to do the same thing on the right. I'm going to take everything on the right up here and I'm going to copy it down here. CO gas, CO2 gas. Then I'm just going to go through and kind of simplify it. If there's anything that's the same on both sides, I'm going to subtract it from both sides. So I'm going to eliminate this because it's the same on both sides. And I'm going to combine those two O2s. So I'm going to clean this up a bit. So I'm going to have this right here on the left, and then on the right I've just got CO2. Now this right here is what we call the overall reaction. When all is said and done, this is a picture of the reaction of carbon with oxygen. You want to, here's an example that's much more extreme. Think of photosynthesis, right? Not photosynthesis, respiration. We could do this with photosynthesis too. You get this, right? Does that happen? What's that? Go ahead. Yep, we're just going to add the delta H's. So right here, delta H is going to be negative 393.5. So I just added those up. If you can add the reactions, you can add the delta H's. Think about the number of steps that are actually involved in cellular respiration. You remember that from bio? It was murder, right? Did you have to remember the steps of the Krebs cycle? You got like 2, 3 carbon molecules, all this kind of stuff, right? That is an example of a huge number of steps. But see, the thing is, if you take all of those steps and you add them all up, this is what you get. This is the overall reaction. And the delta H for this is going to be equal to the sum of the delta H's for all of those little steps all the way around. Glycolysis and the Krebs cycle and the electron transport chain. Right? All of those things, all those little bitty steps, all the steps in the electron transport chain. Add them all up, you're going to get a total delta H equal to this, which is actually the same as if you burn the glucose in a fire. So you just add them up. Now let me just give you an illustration of this with a, let's look at this one again. Let's look at it on an energy diagram. So here's going to be my enthalpy. Enthalpy. Here's what's happening. I've got first my carbon plus 1/2 O2. At a little bit lower level, I've got CO plus 1/2 O2. And then way down here, I've got, I should make this a little lower. Further down, I've got CO2. So basically what's happening is I'm going bam, bam. And this is delta H. This is delta H equals negative 110 and a half kilojoules. This is delta H equals negative 283. And so the whole thing is just the sum. So doesn't that make sense that you add them together? It's like if you walk up the stairs, you're going the same height as if you leapt up to the top landing. Yes? Yep. If you walk up the stairs, so if I walk up like this, right, this is the same as if the difference between here and here is the same as the sum of here to here, obviously, right? So that's what we're talking about. We're just moving around that diagram. So that's Hess's law. Now, how do we use it? Well, it's kind of fun to use. And what we do is it's kind of like a puzzle. So let me just show you one example here of how you would do a problem with Hess's law. You might be given a couple of reactions. So here we're going to give you this reaction. So here I have this stuff is called this is called ketene. And burning this stuff, and I'm going to get carbon dioxide and water. It's a typical combustion reaction. And delta H for that is negative 981.1 kilojoules. Now I'm given another reaction as well. That's the combustion of methane. This is negative 802.3 kilojoules. And then the question says this: what is delta H for methane plus oxygen yields ketene and water? Darn it. Yes, there will be. Yep, there will be a common reactant. So we need to